Hi, welcome. I hope this works and everybody can hear me. I think this should be ICALP track A, session F1. And let's start with a short presentation about scheduling in the random order model, which is given by Maximilian Janke. Can you share your screen maybe?
Okay. So you can all hear me?
Yes.
Then, okay, why worst case scheduling sequences are highly order dependent. This is basically the research of me, Maximilian Janke, and Susanna Albers, my supervisor. So we study the most basic problem of online makespan minimization. Here, a set of jobs has to be assigned to parallel and identical machines. Preemption is not allowed, and we are, of course, considering the online problem. And the goal is to minimize the makespan. So since it's the online problem, we don't know the future, and this prevents us from achieving optimum makespans on arbitrary input sequences. And instead, the common performance measure is just to compare the online makespan to the optimum makespan and look at the ratio. So the question now is on which sequence. And classically, one just considers worst case sequences. That is, one considers this adversary who chooses both the job set and then the job order. But it turns out that in many applications, we wouldn't expect fully worst case job orders. And thus is we want to relax this assumption. Now, fairly popular in many other areas of online algorithms research is a random order model. Here, the adversary still chooses a job set, but the job order is presented uniformly at random. Now, we actually want to propose a new model, which is a nearly adversarial model. And here, the adversary even chooses a job set, but a tiny sub-constant fraction of jobs orders are excluded, which are particularly bad. Of course, if we show a ratio in this model, it will carry over immediately to the random order model. Now, what are our results? For comparison, in the adversarial model, the best competitive ratio lies between the interval 1.88 and 1.92. These are the upper and lower bounds known. And we vastly outperform this by giving an algorithm which for our nearly adversarial model is 1.8478 competitive. And of course, we hope that this will spark more research on scheduling, because compared to other online algorithms, it's not that well researched on a random order arrival. So far, we are only aware of 3 works discussing it. So what are our main technical advantages? First of all, there's a load lemma, which we think will be essential for future makespan minimization research in the random order model, which compares basically 2 time measures, one interesting for algorithm analysis and one interesting for probability theory. On worst case sequences, they don't agree, but after random rearrangement, they do agree. That is, if we look at certain technicalities. Then there's large job magic, which basically tells you that there's no concentration of particularly troublesome jobs, in particular not towards the end, which helps a lot. And finally, we can, in a very subtle way, involve certain techniques from semi-online scheduling into the random order model, which is also very satisfying. So now I thank you for your attention, and I'm hopeful that we can have a great discussion about this.
Thank you. So there is a question which I will just read out, I think, which is it possible to pre-analyze the task received online according to different criteria and then assign them to different machines to further improve efficiency? For instance, would it help to analyze one task every 5 of them to get a better organization plan?
So you mean that we see more than one job in advance and you can assign them?
I'm not sure what it means.
Okay.
I read what is written. Sure, interpret it this way. Why not?
Well, then I actually think you might be the expert on this. At least you research buffer reorderment. I'm not aware on how this helps, at least for our algorithmic approaches, but of course it could definitely, if you have random order model and see certain task.
So the idea of throwing away, say, you ignore 1% of input instances and then do a worst case analysis on the remaining 99% or something like that.
Yeah.
Has this been, I don't really know. Has this been used before somewhere, or is this? I mean, it's a general idea, right? I mean, it seems.
I'm not aware, but I can't say. I mean, so.
Can you think of other problems where this would make sense, or where you think you could do something in such a model? Or?
Well, I think the interesting thing is that scheduling compared to many other problems which are analyzed in random order analysis is that, I mean, if you look at the secretary problem, if you don't choose the right secretary, then you're basically lost compared to the optimum. But this is not the case in scheduling, because even if you make bad choices, I mean, the optimum algorithm has to put the job somewhere. So I think in many random order settings, you wouldn't expect to be good with on almost all input permutations, because in many problems this would already imply being almost optimal.
Right. Yeah. So it wouldn't always help, I guess. Yeah. Okay. Thanks. Let's see if there are any other questions.
I've got another question.
Okay.
All right. So you had lower bounds for the random order model and for the nearly model, and they were differing. And I was wondering, is that some inherent difference, or is that the analysis? So do you have an example where you really have a separation between the two models?
No, I think having a separation would be quite difficult, because that would require us to, first of all, have a better upper bound for the random order model. And I think this is achievable, but we think that the bound of 1.5 is fairly pessimistic. It seems, in general, even randomized scheduling, even there the lower bound is far off from the best upper bound. So I think formally differentiating them should be really difficult. But we, of course, expect that they are different.
Or did you, like, maybe you looked into some toy problems where, like in a completely different context, where you really can separate them? So this might be also an interesting direction.
Yeah, definitely. So, but yeah, I think for this problem, randomization makes lower bounds fairly difficult. So one would have to look into a model where one can actually obtain good lower bounds.
Yeah, thanks. And yeah, I really enjoyed that result. So it's a really nice result. Thanks for your presentation.
Well, thank you for your attention. I'm glad to hear this.
Any other questions from anybody? Okay. Then thank you. And we can go to the next presentation, which is lower bounds for dynamic distributed task allocation by Nicole Wein. Can you share your screen, Nicole?
Yes.
Right.
Okay, is that good? Can
Very
you see
good.
everything?
Yeah.
Okay. Okay, so this 2 minutes, I think, will be just enough time to define the problem. So this work is on lower bounds for dynamic distributed task allocation, and it's joint work with Sinhouse Su. So here's the problem. So we're given a set of tasks, and we also have a set of agents. And the agents need to allocate themselves to the tasks in order to satisfy the demands of the tasks. So we're given a demand vector, which specifies how many agents are needed for each task. So here it's 1, 2, 2, and the agents are allocated accordingly. Now we're studying the dynamic version of this problem. So the demand vector is going to be changing over time, and the agents are then going to have to reallocate themselves to satisfy the new demands. So for example, here you can see we could change the demand vector like this. So what we've done is we're moving 1 unit of demand from task 2 to task 1, and then the agents need to reallocate themselves. So for example, this could happen. So as you can see, when we moved 1 unit of demand from task 2 to task 1, only 1 agent strictly needed to move, but in this case, 2 agents moved. And the goal of this problem is to minimize what we call the switching cost, which is the number of agents that move if a single unit of demand moves. That is to say, the maximum number of agents that move over all starting demand vectors and all movements of 1 unit of demand. So more specifically, what the problem statement is that we're using a problem statement that was introduced by Su, Dornhaus, and Lynch. And what we're tasked to do is to define a set of functions, 1 function for each of the agents. And these functions specify which task each agent is going to be working on. So each agent has its own individual function, which could be different from the functions of the other agents. And the important thing here is that the input to each function has to be only the demand vector. That is to say, the agents are not allowed to communicate with each other. They're not allowed to have memory about the past. They just have to look at the current demand vector and then choose a task for themselves to work on. And because of this, this problem turns out to be at its core not really a distributed algorithms problem, but more of a combinatorics problem, because we're asking, does there exist a set of functions, 1 for each agent, so that each agent can make its decision about what task to work on based only upon the demand vector. And we're requiring that when the demand vector changes by a little bit, then the few agents move. So that's the definition of the problem, and I'll just put the results slide up here. I think my time is up, but I'll just say 1 sentence about the results. In this paper, we proved the first kind of non-trivial lower bounds for this problem for low switching costs. But what we would, of course, really like to do would be to prove switching costs that are a lower bound that's super constant in terms of n and k, and that's what there's new follow-up work that gets better upper bounds and better lower bounds. So that's all for now. Thanks for your attention.
Thank you. Does anybody have any questions? And while you decide, maybe let me ask one. So you said the agents cannot have memory. Now, if you remove that restriction, I guess showing lower bounds already seems challenging. So maybe there's not much to be done there, but can you come up with much better upper bounds somehow?
Yeah, if you allow them to have memory, then you can just get switching cost 1. You can just get the optimal, because each agent could just sort of memorize the whole entire sequence of everything that's happened in the past and make their decision based on all of that information. And so I think the memory constraint is necessary.
Otherwise, okay, so otherwise it's kind of a trivial problem.
Yeah.
I see. Okay. So, and the other restrictions were also necessary, or like, if you change any of them, then.
Yeah, so like, for example, for communication, if agents could communicate with each other, then they could just, whenever a unit of demand moves, they could just run a communication agreement protocol to decide which agent is going to move. So that restriction is also very necessary.
Right. Even if you limit the communication somehow, I mean, you could limit the amount of communication allowed, or.
Yeah, I guess if they have enough communication to run a consensus protocol, then you're good. But otherwise, yeah, otherwise I'm not sure. Right.
And is there any, I mean, log star of k and polylog nk is still quite far away from each other. I mean, is there?
Yes, there's a huge gap, and people should work on this problem.
Okay, great. Let's see. Any other questions?
I have a simple question to understand the problem setting. So if the agents, they have only the global information of the demand vector, so what is the main idea to break the tie of the algorithm?
You're asking a question about tie breaking?
Yeah.
Okay, so this might answer it. So each agent has like a unique ID. And because of that, each agent can sort of run their own function. And so tie breaking can happen based on unique IDs.
But how can the agents know the global information? I mean, if the agent, the red agent is in the first task, and then later when the demand vector changes and etc. So how he gets the information from others to know?
Oh, okay. So this is about so an assumption of the problem is that all of the agents are seeing the demand vector. And your question is kind of about whether that's a realistic assumption or not, okay. Right?
Yeah.
So, well, okay, a little bit of history about this problem. It was first defined actually in the context of ant colonies, like how ants divide themselves up amongst tasks. And it's definitely, as it's stated, it's kind of a clean combinatorial question, which definitely doesn't have anything to do directly with ants. But what they were thinking about in terms of being able to see the whole demand vector was like the ants make their decisions about which task to go to based on some global conditions like the season and the temperature and how much food there is in the colony. And so they can roughly observe these global things about the colony.
Mm-hmm. Okay, thanks.
Any other questions? Okay, then thank you.
Thank you.
And we can go to the next presentation, which is faster minimization of tardy processing time on a single machine, given by Nick Fisher. Can you share your screen?
Sure, I'm on it. Damn it. Can you see it?
Yeah, looks good.
Perfect. Okay. So yeah, this is what it's all about. This very simple scheduling problem, which is called 1 sigma pj uj in standard scheduling notation. So you're given n jobs with processing times pj and with deadlines dj. And the task is to compute a subset j of these jobs and a feasible schedule for these jobs in the subset. Right, your objective is to maximize the total processing time, or equivalently, that's, as we said in our title, to minimize the processing time of tardy jobs, that is jobs which you cannot schedule. I say feasible, and I mean that every job which we decide to schedule actually has to keep its deadline. Right, so maybe this very simple example reminds you of the talk. We're given this red, blue, and green job of these process time respectively, and just the green and the red job constitute an optimal solution, as you can see, because if you schedule these jobs in this order, then both the green and the red job actually keep their deadlines. Okay, now there is a very classical pseudo-polynomial time algorithm for this problem, which was developed by Lawler and Moore in the 60s, which runs in time order n times p, p being the sum of all processing times, so the total processing time. And if you view this algorithm not parameterized both in n and p, but actually in p only, then this becomes order p squared, right? Because you can always lower bound the total processing time by n, as it never makes sense to have jobs of processing time 0. Yeah, and perhaps surprisingly, this algorithm was not improved, at least for this particular scheduling problem, since, well, 50 years, and that's what we do. We show that you can actually improve the running time to O tilde of p to the 7 quarters, right? O tilde just hides a bunch of log factors. Let me give you a very quick proof sketch, more or less meant as a reminder of what I said in the talk. So the idea was that we reduce the scheduling problem via fine-grained reduction to an intermediate problem, so-called max-min skewed convolution problem. This looks nearly as a convolution-like problem, which pops up quite a lot in fine-grained literature, except for this weird thing that on the right-hand side of this minimum, we have this minus I. So we're essentially skewing the right-hand side of these inputs somehow by the left-hand side. This is what makes the problem harder, but what's also necessary in order to solve the scheduling problem. So the next step is to give an improved algorithm for this problem. And as it turns out, the main algorithmic improvement, the main technique which you need is the fast Fourier transform. Right. We also have another theorem which solves the scheduling problem in another regime, parameterized in these other parameters D sharp and D, which are also very natural. But let me not give you any details here. Okay, yeah, that's about it for the summary. Any questions?
Oh, I mean, you said you don't want to give details, but can I ask you for details?
Sure. Yeah, of course.
How should I interpret this exactly? This bound?
So it's just one algorithm, but you can interpret it in two ways. Let me talk about the first one, this P times D sharp bound. D sharp is the number of distinct deadlines in your instance. Okay, and so maybe think about the case where there is just one deadline. So all jobs share the same deadline. Then this problem is more or less the same as a subset sum problem. So you're asking for the maximum value which is attained as a sum of processing times, which is smaller than, well, this unique deadline, right? So not exactly, but something in this sort. And as it turns out, you can use subset sum algorithms to actually solve this problem in, well, in running time n plus the target, which in this case is just p. Now you just need to generalize this to the case where you have several distinct deadlines. And again, it's kind of easy. What you need is you need to combine these subset sums in a way. What you use the sumset operation, which also uses FFT in the end. Not sure. Did this answer your question?
Sure. Yeah. Thanks. Are there any other questions? So, can you generalize this to multiple machines? I mean, this is only for one machine, right?
Right. That's a good question. So, okay, the second algorithm can actually be generalized, I guess, in a nice way. For the first one, we're not so sure, but it would be very nice. I haven't spent too much time thinking about this, but I guess, I mean, of course, you have to open up this fine-grained reduction to the intermediate problem and find out what would be the appropriate intermediate problem then. And yeah, I would guess it gets a little messy. I'm not sure. I mean, we also phrased this as an open problem to generalize this first algorithm, the p to the 7 quarters algorithm, to multiple machines. It would be very interesting, I think.
So it's not straightforward, but no. Potentially possible, or you think it's really not likely that it will work?
To be honest, I cannot give you a better statement than I didn't spend too much time on it. I wouldn't exclude it per se, but yeah.
Okay, fine. So you're doing this max-min skewed convolution. Do you think there are other applications for this, or?
Potentially. I would guess that maybe not this exact version of max-min skewed convolution, but well, the approach for the scheduling problem was just, I don't know, try to reduce it to a convolution problem, and well, let's see what it looks like. Here it turned out to look like this, But I think this general way of trying to reduce problems to convolution-like problems and then use FFT to give improved algorithms, that framework could be used to several other applications as well. Yeah.
Okay. Any other questions?
So I have a question concerning the D sharp. I think it's interesting. I just wonder whether this P times D sharp can even be reduced, because here is the product. Then if I consider the deadline of the different tasks, whether it can be something, whether there's some room to reduce this to the sum of the deadlines, something like that.
So that's actually, I mean, the second bound does that. So if you take D as the sum of the deadlines, so the sum of all distinct deadlines, actually. Sorry. Then you can solve this. You can actually see that this algorithm also solved this the problem in P plus D. I would guess that it's not possible to improve this running time bound to P plus D sharp. No, that actually cannot be, because I mean D sharp is always less or equal than N, right? So actually we would improve the running time to P, and this seems far out.
Yeah, I see. So D is the sum of the deadlines. Okay. So
D, right.
Yeah, it'd be interesting. I mean, the two terms. So for what cases are the first term larger and the second? So is there some characterization of this?
I guess you can always come up with instances. I mean, for instance, in this first term, as I said, if you have just very few number of distinct deadlines, so a number of jobs which have to finish at the same point in time, then of course the first term becomes very small. The second term, I guess, is if you just consider a small range and want to a small range of jobs, like well, deadlines are small. Yeah, you can, in any case, you can construct instances where these running times become much better than the original running time of N times P.
Yeah.
Okay. Anybody else? Any more questions? Okay, then thank you very much.
Thank you. And
let's go to the next presentation, which is breaking the barrier of 2 for the storage allocation problem. Tobias Mümke.
Yeah, hello.
Way ahead of me. Okay.
Sorry. Yeah, thanks for the introduction. I'm Tobias Mümke, and I will present our paper, Breaking the Barrier of 2 for the Storage Allocation Problem. And this is a joint work with Andreas Wiese at University of Chile. So what's the storage allocation problem? It's a problem where we want to allocate tasks. So there's some start time, some end time, therefore there's a width, and then there's a certain demand. So the way that we depict that is a rectangle. The rectangle goes from left to right, that is the time that it takes. And from bottom to top, this dimension of the rectangle that depicts how much demand we require for that. Then there's of course also a weight. And the units that I wrote in this picture come from the original meaning of this problem. It comes from allocating storage over time. So if we want to allocate 6 megabytes of memory for 15 minutes from this start point to this end point, we gain a profit of €2. If we don't schedule it, we just lose it. And of course, there's not only one task, there are many tasks. So these tasks are rectangles and they are stacked on top of each other. It's more or less like playing Tetris, only that we choose the order and we choose which tasks we take and which ones we discard. So what you can see is that these tasks are really drawn as rectangles. The reason is that if you have really a storage allocation, you don't want to reallocate. So the storage that you use that starts here and ends here, and you need really that storage for a whole amount of time. But this also appears in many different situations. So if you allocate a car in a car rental context, then you also don't change the cars over time. So it's a very reasonable thing that you actually have these rectangles here, that they're really depicted as rectangles. And of course, you have a capacity, that is the red task cannot be scheduled because it would exceed the capacity. But we can rearrange the tasks such that it can be scheduled. So if you compare it, we have the very same set of tasks in both cases, but if we rearrange them, then we can schedule more. And this is actually also a difficulty that comes into this problem compared to some other very similar problems. And if we have a line on top, like drawn here, then we talk of uniform capacities. That is a classical definition of that problem. And this is actually also the practically most relevant one. But more interesting from a theoretical point of view is, of course, if we have some more complicated profile, because that gives a lot of more depth to the problem. So, and the other problems that I was talking about is unsymmetrical flow in a path and the two-dimensional knapsack problem, because the storage allocation problem, SAP, can be seen as a combination of the two of them. Because unsymmetrical flow in a path is the very same problem, only that the tasks are not drawn as rectangles, so we only care about the total amount of capacity used. So we can imagine that we push the task down all the way to the bottom. On the other hand, the two-dimensional geometric knapsack problem, so geometric should be written here, we have the same situation as for the storage allocation problem, except that we can also move the tasks to the left and to the right. For both problems, there was a two approximation, and the barrier was broken like at Stock 2018 and at Fox 2017. But due to these extra challenges that we have in the storage allocation problem, this was really not easy for the storage allocation problem. And yeah, therefore 2 plus epsilon was until recently the best known, actually 2 plus epsilon was the best known result for that. And that was still the case if we had quasi-polynomial running times. This is interesting because for UFP, for quasi-polynomial running times, we have a p-task, and so we have a q-p-task. And this we already have since quite a long time, but for the storage allocation problem, we do not have that. The results that we presented or that we obtained was that in polynomial time, we could break the barrier for the storage allocation problem if we have uniform instances. So for the practically most important case, we actually broke the barrier of 2. When we looked at the more general case where we have quasi-polynomial capacities, there we were able to break the barrier in quasi-polynomial running time. The technique that we use is closely related to resource augmentation. And if we really allow resource augmentation, that means the optimum is more restricted than we are. We have some extra capacity that we are allowed to use as an algorithm. Then we got 1.5, roughly 1.5 approximation in polynomial time, and we got a q-p-task. So, and this is for arbitrary instances. So in quasi-polynomial time, we actually closed the gap in this sense. So, but what was known for UFP a long time is not also known for SAP now. But with resource augmentation, so it's not the very same thing. So it's actually much weaker. And why do we have this barrier between 2 and better than 2? Like we distinguish between small and large tasks. And it's easiest to understand if we just have uniform capacities. If we are below some delta times the mu times the capacity, then we are small. If we are above some delta times the capacity, we are large. The tasks in between we remove, and each separate problem we can solve. So what was known is that we can get a p-task if we have only small tasks. We can get a p-task if we have only large tasks, but combining them was always a problem. And if we, I think I'm quite running out of time already, but if we get half of the profit from large tasks, half of the profit from all small tasks, then we get a 2 approximation because we get the half of the overall profit. So these bars depict that the large tasks, like in an optimal solution, the overall weight of large tasks that we collect, that is the box on the left. And on the right-hand side, the red box is the overall weight that we collect from the small tasks in an optimal solution. And since we can solve these cases separately, the worst case appears if these weights are the same. And the key thing that we did, and like what actually helps to get better than 2 is if you get all of the large profit, but a little bit of the small profit, then you are better than 2. And the same the other way around. If you get all of the profit from small tasks and a little bit more from the large tasks, then you also get better than 2 by combining it with the old results. So, and this is what we achieved. There is a notion of boxed solution. So the rough idea is that we put the small tasks into boxes, and then we are able to schedule the boxes. And then we were able to identify actually a quite large number of different situations where we get a boxed solution in one way or the other. This way, we were able to solve the uniform cases. And for the not uniform cases, there was one case where we were not able to obtain boxed solutions. So that's a situation where we cannot really throw away anything anymore. That on the left-hand side, we have some profile. On the right-hand side, we have large tasks that also create a profile, and we cannot afford to remove anything anymore. And what you can see is that the small tasks are very limited. They are in a very narrow range where they can actually be scheduled. Here we combined, so we obtained a linear program that can actually deal with the situation with some actually not so easy rounding. So to summarize, the factor 2, even for the general problem, is not the last word. For the uniform capacities, we really broke the barrier of 2. And the question is there a polynomial time approximation scheme for the storage allocation problem? So this is the main open question that we have, not only for this problem, but also for the related problems. And we know that it's true if we have resource augmentation and quasi-polynomial running time. And another thing that we obtained is, like for the general capacities, I think one of the most interesting ingredients is that we obtained a new technique to combine small and large tasks. And I think this might be useful for other packing problems. So another open question is, can we find other problems where this plays a role? So thank you for your attention and thank you for listening.
Thank you. Are there any questions?
I have a question, Tobias. I wonder the number of boxes that you apply. How is that determined?
So the number of boxes. So what the idea is that the box takes the role of a large task. And the large task, there can be only few large tasks. That is, if you look at the definition, a large task is larger than delta times the capacity, and delta is some small constant. So there can only be 1 over delta tasks being stacked on top of each other. And then the size of the box is like at least delta times the capacity, so the height of the box. So what I did not say is large means the y-axis. So the capacity used is large. And small means the capacity used is small.
Okay, thank you.
So for generalized capacities, you have this kind of weird shape and with the capacities, but the tasks themselves are still rectangles, right?
Yes, that's right.
So what if the tasks are not rectangles?
If the tasks are not rectangles, I suppose it's getting much more complicated still. So right. I have not thought of that at all, actually, because like rectangles are already super hard to deal with. But it's actually a good question because in other contexts, like independent set of rectangles, there are some generalizations where it's not rectangles anymore, but more general shapes. So it definitely would make sense in this context.
And right, so obviously it's much harder, but I mean, are there somehow impossibility results that don't apply to rectangles or something like that? Or?
I'm not aware of any. What I suspect makes a difference is how many changes do you have? I mean, you could think of like not completely rectangles, but some shapes that have sort of a simple structure that there are only few changes among the x-axis. So then like suppose the demand changes over time, and this is sort of some bumps that go to the top. So it's only a constant number of bumps. I don't see real limitations of getting a good result. But if this becomes super constant, say like square root n or so, then I think it could get really complicated. But maybe you could still do something, because in the end of the day, you will guess some profiles that sort of discretize what you have to memorize. So maybe it's even possible, but I don't know.
Okay, Thank you. Any other questions?
So I have further comments or small questions. It's quite interesting. I wonder whether you have applications like power supply, and in particular power, wind power, and etc. That's for me it fits the problem setting.
So this problem, I mean, I was studying many related problems, and some of them have applications even in space, and there are some interesting things going on. This particular problem actually appeared when I was once working with a company. I was not working with a company, but we were cooperating with a company for car sharing, and it really appeared there that they had cars that had to be scheduled. So the customers were really renting the car from a certain point in time to another point in time, and this was really giving a time window where this car had to be scheduled. It's a much simpler problem in a way because you have only few cars, and it's sort of it's a strongly simplified situation. But it still became interesting because you can have situations that a car is blocked. The car needs some maintenance, and then the car really has to be scheduled in this block, and you don't have any allowance anymore.
Thank you.
Okay. Thank you. Okay, thank you, Tobias. Let's go to the next presentation, which is the online min-sum set cover problem, and it's given by Stratis Golakis. Can you share your screen?
Are you seeing my screen now?
Yeah. Can you do it full screen? Yeah.
Yes, yes, of course.
Great. Thank you.
So, this is joint work with Dimitris Fotakis, Lukas Kavouras from National Technical University of Athens, Grigoris Koumoutos from Université Libre de Bruxelles, me that I come from the Singapore University of Technology and Design, and Manolis Vardas from the TSH Zurich. So, let me introduce you to the problem. So, we started the online version of the min-sum set cover problem. I'm just going to give you the definition of the online problem due to lack of time. So we are just given a set of elements, a set of n elements, and so at each round t, a request RT that's a subset of these elements arrives. So our task is to select a permutation pi t of the elements, and once we fix a permutation at round t, we pay the following cost. We pay an axing cost, or can be seen as a service cost, that is the first position of the element RT at the permutation that you have selected, this is the axing cost, and plus the switching cost for converting permutation PT minus 1 to permutation PT, which is the number of inversions, that's the number of inversions between the two permutations. So our overall goal is to minimize our overall goal is to design an online permutation selecting policy, such as we minimize the total axing cost that we suffer plus the total moving cost. So basically, we have the following results. For the case, at first we designed a deterministic online algorithm that is based on the multiplicative weight update algorithm. Actually, it's an online de-randomization scheme of the multiplicative weight update algorithm that with the property that if the cardinality of the request is bounded by a fixed constant, then R, then the algorithm is theta of R times the cost of the optimal static solution. And this means that this is the cost of the best the cost of the solution that fixes a permutation up front and keeps the same permutation all over the rounds. So it just pays axing cost and no moving cost because no switching between the permutations performed. So this is a slightly more easy benchmark to achieve. But however, this is that we prove that even against this easier benchmark, you cannot achieve better than theta var. And for the more general benchmark, which is the dynamic optimality, compared with the optimal solution that can switches permutation from round to round, we present a very simple move to front kind of algorithm. Actually, the algorithm is just take the elements of the request, move them uniformly on the left until one of them hits the beginning of the permutation. And we proved this bound R over 3/2 square root of n And so obviously this is much higher than the other, but the benchmark is much more difficult. So these are key results. And let me tell you some future directions that our work leaves open. So it will be very interesting to understand there is a huge gap between the lower bound for the dynamic benchmark and our current upper bound, because there is this dependency on n, which is the number of the number of the elements. And then it would be interesting to understand the relationship between the optimal dynamic solution, the optimal static solution in atom generated distances. We guess that there is a constant approximation between the dynamic solution and the optimal static solution if we add noise to the request sequence. And finally, it will be interesting to try to derive offline algorithms against offline approximation algorithms with respect to the optimal dynamic solution. We currently do not know any kind of these algorithms. So these are basically our results. Thank you very much.
Thank you. Are there any questions? So I mean, I was wondering about the cost function somehow. So if I understand the problem correctly, the cost is the position of the first element in the permutation that is contained in the set. Is that right?
Yes. So yes.
So what about other type of cost functions? For example, the average position, or you could have weights, like a weight for the first position, the second, and so on. Maybe they're decreasing or something like that.
So you multiply. Actually, there is a generalization of the problem. That's the generalized mean-subset cover problem, where you pay each request has a different requirement. This is another objective that is already studied, and you pay until the position where the covering requirements of the request are covered by your permutations. So this is another a clear generalization of the problem. In case you pay the average position, I have a feeling that the problem is easier, but I'm not quite sure. This is just a guess.
Okay. So you're not. This hasn't been studied, or yeah.
I'm not sure, but I don't think so. If you pay the sum of the positions, probably I have a feeling that the problem is it might be easier. The thing is that we don't define this metric. This metric comes from this objective comes from the mean subset cover problem that has already been studied.
Mm-hmm. Yeah.
We just studied the online version.
Just a comment, like in the offline version, what you ask, it has been studied as the generalized mid-subset cover, but yeah, for the online, there is nothing known.
I see. Any other questions? Okay, thank you very much. Then let's go to the last presentation, which is online algorithm for weighted paging with predictions by Kevin Sun.
Hello.
Hi.
Hello, is this good?
Very good.
Okay. Yeah, hi. So I'll be talking about weighted paging with predictions. This is joint work with Rahul Jiang and Demoy Pendergrahi, who are both actually here. So the paging problem, as many of us know, so there are n pages and we have a cache of size k, which is less than n. It is online, so at each time t, a page p is requested. If it's in the cache, then we don't have to do anything. But if it's not in the cache, then we have to pick a page in the cache to evict. We then have to fetch the requested page into the cache. And the goal is to minimize the total number of evictions. And in the weighted version of the problem, every page P has a weight, and the goal is to minimize the total weight of evicted pages. So we measure our results with the well-known competitive ratio, which is the ratio of the cost of the algorithm against the optimal offline cost. So I'll just briefly go over this. For the unweighted version and the weighted version, the situation is the same. For deterministic algorithms, the best algorithms are O of k competitive, and there are also lower bounds. And then for randomized algorithms, we get log k competitive. So in some sense, this problem is is solved. But now we consider the problem of what if we have predictions about the future? And this is kind of in this recent line of algorithms with predictions. So how do we extend online algorithms with predictions? Can we prove better competitive ratios about them? So before we begin, we have to establish what does it mean to predict the future for our problem. So there have been two prediction models that have been studied already. So one we call this per request prediction, or PRP for short. This was introduced by Lycoris and Vasovitsky in 2018. So it says on the arrival of page P, the prediction tells us the next arrival time of the page. So for example, if our cache currently has 4 pages, A, B, C, D, and so now it's time 5, the current request is B, and the future looks like EBA, EDECF, then PRP will tell us the next arrival time of B, which is 7. And since A, B, C, D were the first 4 requests, we also know the next arrival times of everything in the cache. So in particular, A is 8, D is 10, and C is 12. We don't know the next arrival time of E because it has never arrived, and same for F. The other prediction model is called L-strong look-ahead. This is introduced by Suzanne Albers in 1997, which says at each time T, the algorithm can see the current request as well as the next L distinct requests. So in this same example, we see the current request B, and we also see EBA, the next 3 requests, because we exclude B. If we see in too strong look ahead, we see the next 2 distinct requests, not including the current request B. So what are the known results for unweighted paging with these 2 prediction models? So if we go back to PRP, which for each request, you see the next predicted arrival time. Lycoris and Vasovitsky gave an algorithm whose competitive ratio satisfies 3 desirable properties. So as the error in the prediction decreases, so for the error is suitably defined. I haven't defined it, but for some measurement of how good this prediction is. As the prediction gets better, our competitive ratio gets better, or their competitive ratio gets better. If the error is 0, so if the predictions are always completely correct, then this is constant competitive. Note that all 3 are simultaneously satisfied. So if you knew that the predictions were correct ahead of time, then you could simply perform Belady's rule, which is the offline algorithm. And the third one is that this is always log K competitive. So it's never worse than the best online algorithm without predictions. And the number 1 was improved by Rohatki in 2020. For the other model, L-strong look ahead, so assuming that all the predictions are perfect, so the next L requests are exactly correct, then Albers improved the competitive ratio from OK to OK minus L for deterministic algorithms, and for randomized algorithms, improved from log K to log K minus L. So these are all for unweighted settings. So we want to consider the same problem in the weighted setting. So our first result is a lower bound, which says that these 2 prediction models yield the same asymptotic bounds as algorithms without predictions. So in other words, even if they're perfect, we cannot do better than we cannot beat the lower bounds for algorithms without predictions. So even if we have for weighted paging, even if we're given the predictions are perfect, any deterministic algorithm must be at least K competitive, and any randomized algorithm must be at least log K competitive. So to overcome these lower bounds, what we do is we introduce this a third prediction model, which in essence combines the previous 2. I won't give the details, but basically you can see everything that both of them can see. And so this one we call strong PRP. So it combines strong look ahead and PRP. And for this one, we prove that if this prediction model is completely correct, then we get a 2 competitive algorithm. And but we'd also like to analyze how does this do if it's not completely correct. And for this, we give various upper and lower bounds. The definitions of the errors are somewhat technical, so I don't give the details, but we give various upper and lower bounds on what happens if this prediction model is not completely correct. I'll just briefly mention some future work. So one is to find and analyze other prediction models. So in particular, all three of the models I've talked about for paging, they enable seeing arbitrarily far into the future, which might not be realistic. And so it would be interesting to see if there are more realistic prediction models for paging that we can also prove performance ratios, competitive ratios about. And the second thing is to kind of generalize where predictions can be applied in different algorithmic frameworks. So I'll say one limitation of our work is that the optimal algorithm for weighted paging, given by Bansal et al. In 2007, it solves and rounds a linear program online. And so we've seen it'd be interesting to see how can we incorporate predictions into this process in order to obtain a truly robust algorithm. By that I mean our algorithms are not truly robust in that if the error is high, the performance can be high, can be bad. But if we're able to solve this, incorporate predictions into the solving and rounding procedure of a linear program, then perhaps we can also get a weighted paging algorithm with predictions that is never worse than O log K competitive. And yeah, that's the summary. Thanks.
Thank you. Do we have any questions here?
Yeah, so I have a question.
Mm-hmm.
So you said that you don't give any bound, any algorithm which is log K competitive and also has some nice ratio depending with error, right?
Yeah.
Yeah. So, but you know, there is kind of possible to use like a multiplicative weight update between two algorithms, like take the worst case algorithm, this primal dual algorithm, and what you have here, and this will give immediately like what you said in the last slide, right? So
right.
One can get an indirect way of having both like log K competitive and you're bound for the error.
Right. So we have tried this idea of kind of switching around between two algorithms, and so like if the cost of one gets too high, then switch to this other one. And I guess there are some trivial ways to do this. So for example, if we go really trivial, then you just use their algorithm. But we weren't able to kind of nicely incorporate the switching idea.
Yeah, so my point basically is like just do it in a black box fashion, like just run multiplicative weight update between the two algorithms, and whatever is the probability that you get for running algorithm A or B, you just use the probability. So you don't have to do it, you know, in an ad hoc way for your specific problem, just you know, to use it as a black box. So this should work, I guess.
Right. Yeah, that should be interesting. This works. Yeah.
So this problem with prediction errors, I mean, depends a bit on how you define what a prediction error is, right?
Right. Right.
I mean, can you think of any like somewhat reasonable notion of prediction error that maybe would help you to get a positive result? I mean.
Oh, right. So if you define the prediction error very loosely, you're right in that you can get nice results very simply. So, but I guess the challenge is, so in fact, there's been recent work in ICML this year actually that kind of considers other prediction errors, because so for example, if we look at the so Albert has never considered the error. So if we look at the PRP error, the error that they consider is basically the sum like of the absolute difference. So it gives you a predicted next arrival time, and you just take the difference of that with the actual next arrival time, and you sum this across all requests. And so one, I guess, drawback of this way to measure the error is indeed if like all the predictions are just off by one, qualitatively, maybe we wouldn't say that the predictions are that bad, but but quantitatively, this will actually accumulate over time. And so we actually do consider sort of like a edit distance version of the error, which overcomes this. So in this situation, the off by 1 error, our edit distance error wouldn't be that high. But as we already know, even for this edit distance, we weren't able to obtain a robust algorithm, but we could scale in the edit distance version of the error. And so it'd be interesting to see if we can, get the best of both worlds.
Yeah. Okay. Thank you.
Right.
Are
Thank
there any more questions? Well, if not, I guess that concludes the session F1. And thanks all for coming. We finished just in time. And enjoy the rest of ICALP.
Thank you.
Thank you.